Good afternoon and welcome to the Galactic Centre Star Party Q&A session. Before we begin, I would like to say that in the spirit of reconciliation, the Astronomical Society of Victoria acknowledges the traditional custodians of country throughout Australia and their connections to land, sea and community. We pay our respects to the elders, past and present, and extend that respect to all Aboriginal and Torres Strait Islander people today. Today we bring you the second last stream for the weekend. It's been a busy one. Today we have some of the best and brightest minds in the world of astronomy. They may not think that, but I do, and that's what matters. However, as always, let's get the formalities out of the way before we get stuck into probing the minds of our panel. If you're enjoying today's stream on Facebook, you can donate stars. All donations, no matter how large and small, are welcome, and those on YouTube can donate stickers. If you're watching us for the first time, don't forget to subscribe and follow our Facebook page and our YouTube pages. Now, with all the formalities out of the way, it's time to bring in the team and see what we can learn. We have with us today our ASV ambassador, astrophysicist and media star, Claire Kenyon. I'm calling her a media star now.
Kind.
That's all right. We also have ASV member and our own personal book of knowledge, Stefan Nebulae.
Hey guys, glad to be here.
PhD student at University of Melbourne and Wednesday nights speaker from for the ASV, Stephanie Bernard, and Associate Professor of School of Physics and Astronomy at Monash University, Paul Lasky. Good afternoon, everybody.
Hello, everyone.
Hello.
All right, so the format today essentially is for those who are watching, if they have questions they'd like to ask you guys. We have some questions that have been sent in, but if anybody watching has a question, please pop it in the chat and we will pop it up and ask the questions. And there we go, the first one's already come through. And we'll ask the question and whoever can answer it for our viewers. So Hayden Purcell has two questions. When we say the universe is expanding, which part is expanding? Dark matter. And part two is, if we flew into a nebula like the Trifid Nebula, would we see pink all around us? So who would like to have a go at answering that one?
I can take a stab at the first part. So when we say the universe is expanding, what we're really thinking is the whole space-time around in the universe. So we're here on the Earth, and so the Earth is held together basically by gravity, and so we don't have to worry about our Earth expanding because it's held together, but it's sort of the whole the whole universe is moving apart, basically everything moving apart from each other, but because gravity,
Steph, your internet's dropping out a bit, Steph.
Is a
Steffi,
force that affects basically, everything in the universe.
Whoa, we're having a bit of lag there, Steffi.
Else, it's just a different sort of strength.
May as well start with some cool problems.
Why not? Did one of you guys want to jump in while we try and get Steffi's tech issues sorted out?
Yeah.
I'm happy to have a go.
Yeah, go for it.
Sorry for Steffi because she's so good at explaining this stuff.
Exactly.
It really is. I know.
This is galaxies.
I'm not even sure she can hear us.
They're all held together.
She's coming back.
No,
well, maybe I'll start with the first bit then, if you'd like.
If you could, yeah. She's she'll have to come back in. Go for it.
So I think what Steffi was trying to say, which is Steffi was trying to tell us about the fact that the Earth itself is not expanding because it's held together by gravity. And in fact, that's probably much the same as other things that are held together with gravity, solar systems and whatnot. When we talk about the universe expanding, we're actually talking about the space between sort of galaxies or clusters of galaxies that aren't gravitationally held together. That space is actually increasing. So the space itself is growing in between objects that are held together by gravities. The force itself that holds gravity together is enough to overcome this expansion. So don't worry, we're not all getting bigger, although during COVID, I must admit that I've been having my own little expansion. But don't worry, I'm not pregnant. I've just been eating my way through lockdown. So so it's actually the space in between things that are gravitationally bound. The space in between is actually growing. It's time now than there was 10 minutes ago. And Paul, I reckon you've probably got your thumb on this more than anyone here, I reckon.
That was a beautiful description, though, Claire. I was fearful we were going to lose you as well. Then we're just going to start dropping like flies with the internet. But no, that was a beautiful description. So absolutely, it's the space that is expanding. It's the distance between any two given objects is expanding. So in principle, Claire would expand independent of how much she ate. But as Claire said, the forces that are holding her body together are actually stronger than the amount of expansion that's happening. So this is not relevant on the scale of a human. It's not relevant on the scale of the Earth. It's not relevant on the scale of the solar system or even our galaxy, but it's only relevant on the scale of many galaxies. And when you think globally like that, then we know that the universe is expanding. And the further away they are, the faster away they're moving.
Now, who would like to answer the second part of that question? If we flew into a nebula like the Trifid Nebula, or like my Trifid Hair Nebula, would we see pink all around us?
Is that the singer?
I don't know if we want to see the singer pink, but the color pink.
Oh, right.
So there's a lot of pink when we see astrophotography images. There's a lot of pink and blue in Trifid. So I think that's what he's asking. Would we see that if we flew through it?
So I guess I can take a stab. As an astrophotographer, I can sort of give my explanation, and then the experts can elaborate a bit more on the physics. So as far as my understanding goes, these objects, these nebulae out there in the universe, have a very low intrinsic brightness. They're just very, very dim objects. They don't emit a lot of light by themselves. And this is really obvious if you've ever even looked through a telescope, even like the big one you see behind me. When you look at it with your own, human eye, even with big telescopes like this, these objects are incredibly dim, and we don't even see the color for most of them. If I were to look at this, at the Trifid Nebula with this telescope, I would see no color at all, even in the darkest skies. That's because they don't emit a lot of light. So even if we were to fly to them, their brightness wouldn't be, enough for our eyes to pick up. And there's an extra complication in that there's something called the conservation of luminosity. And so the object in the night sky is really, really small, and it emits, an amount of light that we can pick up with our telescopes. But if we were to fly towards it, that light that's taking up just a small piece of the night sky is now spread over a very, very large area. And so the amount of light, the flux that our eyes can pick up, is now spread over a massive area. So any given amount of that light is much, much smaller. So even for some of the brightest nebulae in the night sky, like M42, which we can just about see with our naked eye, if we were to fly there and immerse ourselves within it, that light would be spread out so much that we probably wouldn't be able to see it at all.
A very good answer. And on that note, I think it's time for the next question. I'm not sure who's going to be able to answer this one. Ian wants to know, can we draw some form of the Penrose diagram with coordinates showing the difference between expanding universe compared to, and he's got a second part to that, compared to one where expansion is accelerating?
I can have a crack at that.
Go for it.
So I'm going to start off by putting a caveat out there that there's Penrose is incredibly creative, and so there's about a whole bunch of different things called Penrose diagrams, and I'm going to have a crack at thinking which one you mean. So I think this is referring to space-time diagrams where you draw the time on the vertical axis, so time going up and down, and you somehow draw space in a horizontal axis. And you can think about various space-time geometries in this way. I believe that you can absolutely represent expanding universes in these diagrams, and you can absolutely represent accelerating, expanding universes in these diagrams. And it's actually very helpful to do that. Now, the geometry is very complicated, and so it makes these diagrams very complicated because when the universe is expanding or accelerating, you no longer have straight lines representing the speed of light, for example. So we're now getting very technical, and I probably don't want to go so technical. I just taught a third-year class on cosmology, and we didn't even go into this kind of stuff. So I think this is kind of fourth-year honors level type of work. So I think the answer is yes, you can represent them, but it's complicated.
Did anybody else want to add anything to that? And Claire, your internet seems to have cleared up nicely now as well, so we've got you back as well. You're not blurry anymore. Anybody else want to add anything to that, or shall we move on to the next question? Because we've got quite a few coming through. We've got, here we go. Harry wants to know, I'm trying to understand how come the Andromeda and Milky Way galaxy would merge after some time if the space between galaxies are expanding.
I can take that one.
Yep.
So this is sort of what I was trying to explain before. My internet went really bad. So while the universe is expanding, and so space-time, everything is moving apart from each other in all three dimensions. Because we have gravity, and this is one of the fundamental forces of the universe, gravity is acting. Every atom in the universe, it feels a gravitational force from everything else. It's just that the strength of that is very, 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 very small for most things. It's only on the sort of most massive objects that we really feel the gravitational force. So because galaxies are extremely massive, they're billions of times bigger than our own sun, they have very, very strong gravitational sort of pulls. So the Andromeda galaxy, which is our closest large nebula, and Milky Way are both very large galaxies. So they're feeling a gravitational attraction between them. And this is actually sort of overcoming that expansion. So they're still going to be merging and moving together, even though the space is expanding between them, just because they're just so large that that gravitational pull is very strong.
Mark, if you're talking, I think you're on mute.
Yeah, I am on mute. Sorry. Ian wanted to know if there are any good references. He had his fourth year honours back in 1969.
That's my trick. That's my trick, Mark.
I know. It is your trick to talk when it's muted, and I stole it from you. So, Paul, that one I think is aimed at you because you were talking before saying you did a third year's. Oh, look at that. An introduction to modern cosmology by... Who is that?
Andrew Little.
Andrew Little. There we go, Ian. There's a book for you to go and get.
So I have this here because, as I said, I just taught it at the end of last semester, and this is a sign of how messy my desk is. These things don't move. But it's an excellent book, and so if you, it is technical, but it's technical in a really nice way. It doesn't go through all of the hardcore general relativity that you need to understand cosmology. It does it in a simpler way, and it's a nice book in that you can actually skip over a lot of the equations if you like, and you'll get the idea of the physics without necessarily being able to solve the problems yourself. And so then you can go back and understand the equations, and yeah, there's a nice iterative way of doing it here. But highly recommended. That's the one we use. Am I allowed to plug Monash? I guess it's too late.
Yeah.
That's the one we use in our Monash undergrad course on
There
cosmology.
we go. That's insider trading information for anyone who's looking to get into astrophysics, huh? Now, here's a nice, interesting one because it will have a different answer for every one of you. What was one fact that blew your mind the most or radically enlightened you about what's happening in space? So each of you can have a go at answering this one. Claire can't because she looks like she's frozen.
It's sitting really still.
She's sitting very, very still. Internet is not playing kindly for anyone today. So we'll start with you, Stefan, and then I'll work around. We'll go Stefan, Steffi, Paul, and if Claire comes out of her frozen statue stage, we can get her to answer as well.
Sure. So again, I'll give a bit of an astrophotographer's perspective. So as an astrophotographer, what we're doing is taking images of space. And a lot of the time, that's all the general public sees, right? Are these images, beautiful images of galaxies and globular clusters and nebulae. And it becomes easy to think of space as this big static thing that's just never changing. And to some degree, that is true, right? On the human lifetime time scale, space really doesn't change that much. But one thing that really changed my perspective of the universe is trying to think of it in the long term, on the cosmical time scale, and to imagine that the images that you're seeing aren't static, right? Those objects are constantly dynamically in motion. Galaxies are constantly, revolving, or there are, waves of density that move through them. Globular clusters aren't just big blobs of stars. They're, like chaotic, beehives constantly moving with, really strange orbits, stars moving in and out of the center. And so that's one thing that I'd like to pass on to people. When you see a beautiful photo of space, don't see it just as a static snapshot. Try and imagine that object as it really is, evolving over time.
All right, Steffi, it's your turn now. What is one fact that blew your mind or enlightened you?
Yeah, so mine, if any of you were at the talk on Wednesday, I sort of briefly mentioned this, but one thing that I learned when I was in, I think already in graduate school learning about cosmology. So we have this thing when we're looking at the sky called the angular diameter of an object. So the way that I teach my my students this is if you have like an object like a galaxy, which has some visible distance, and you're sort of shooting out a laser to one side of it and then another laser to the other side, and the angle that those two lasers are making is called the angular diameter. So as we go back in time, basically further away from us, as we would expect, that same physical size starts to get smaller and smaller. And same way that if you have a car in front of you on a highway, the two headlights are going to start to look, closer and closer together as it gets further away from you. But because of the way that the universe has been expanding and the history of the expansion of the universe, basically, we have this thing where, as we expect, the angular diameter gets smaller and smaller as we get further and further away. Well, there's actually a point in the universe where things start to get bigger and bigger. So they start to look bigger and bigger on the sky, even though they're getting further and further away. And this is called the turning point. And it really just blew my mind, basically, because it is so alien to what we would expect here on Earth. But it's just due to basically the sort of, the way the universe is expanding, the fact that the speed of light is constant, we can actually use basically where this point happens to get some information about how the universe has been expanding in the past as well, which is, part of this observations feeding back into theory, which is really interesting, I think. Yeah.
I think that puts it to you, Claire, now that you're back in the world of the non-frozen screen. What is one fact that blew your mind the most or radically enlightened you? What's happening in space? And that was Steffi.
Space Cat.
Space Cat. Space Cat. Hi, Steph's kitty cat.
Nothing's going right today.
It's a
I'm
fun one
assuming-
today. We're keeping everyone on their toes. That's what we're doing.
Well, I have reset my internet, so hopefully that is better. I know. Yeah, so actually for me it comes down to much less of a fact or sort of an astrophysical concept, more just, I think, with all my work with the public and telescopes and all that sort of thing. For me, I mean, I used to be a geologist, so I'm for a little while, not for very long, and I always was just blown away by the sense of time and the sense of scale, from the sense of you've got these big mountain ranges and you can pick up tiny grains of sand on the beach, or even just the scale of trees compared to humans, and then you've got all the way down to microbes, and the sense of time between. I think I saw a funny meme the other day that was when people. It's more accurate to draw a Tyrannosaurus Rex on a powered unicycle than it is to draw a Tyrannosaurus Rex and a Stegosaurus in the same picture. So the fact is that there's so much more time between the Stegosaurus and Tyrannosaurus Rex walking the earth than there is between the Tyrannosaurus Rex and powered unicycles. And for me, that was this enormous sense of time. And then when I sort of shifted to astrophysics, I sort of realized that even that is just a blink of an eye. What's happening on Earth and the sense of scale of time and of space, I think, is the thing that continually blows me away. Everything from the very small to the very large, it's almost impossible to comprehend. And I love the way we talk about things as if, we have any way of really grasping what billions of years actually is. And knowing that light's come from something and traveled for 1,000 years just to go into your eyeball from a source that you can only sort of imagine is there, or your brain is registering as being there. I just find all that so awe-inspiring and very confusing, I think, but in a great way. Yeah.
That moves us on to you now, Paul.
So I guess a thing for me, and this comes out of some of my own research. So I do research into things called gravitational waves, which are these little ripples of gravity that travel at the speed of light, and they get generated by huge moving objects or accelerating objects. And one of the things we observed with gravitational waves back in 2015, two black holes that collided with one another. And the amount of energy that came out in gravitational waves from that one collision was the equivalent of taking three of our suns and just completely turning all of that mass into pure energy in the way of E = mc squared. So the way a nuclear bomb goes off and it uses a tiny, less than a gram of converted energy, this is actually taking 3 times the mass of our sun, converting that into pure energy, and that's the energy that went into gravitational waves from this collision. And then the sort of add-on to that, so that's remarkable in and of itself for mine. The add-on to that is the measurement that we made to actually detect that thing, was that we have these 4-kilometer arms or 4-kilometer length tubes, and we measured a change in that length of the order of 1/1000th the size of a proton. And so that's how much the gravitational wave changed the length of that arm. That's what the measurement was. And yet there was this 3 solar masses worth of energy emitted in this huge explosion. So for me, I can't get my head around those numbers. I know them. They're ingrained and imprinted in my brain, but I can't get my head around them at all.
I don't think anyone else can follow that. I mean, for me personally, it's just being able to look through a telescope in the backyard with all of the light pollution that we have and still see things like Tarantula Nebula. The fact that I can do that in my backyard, that to me is just so powerful and mind-blowing. Anytime the clouds aren't around, when I can just lift it up, put it out there, look through it and go, I can see stuff that's nowhere near me. even with all of those lovely neon and LED screens around the Nepean Highway, South Road. I can watch TV from my roof if I wanted to, but yeah, just to be able to do that is so cool. Nowhere near as fancy as what you guys were talking about. Very basic, but still very exciting. And I love it when Sadie comes out with me and she'll get a pair of binoculars and just stand there and just look through the binoculars. That's a pretty powerful thing as well. Now, we've got another question here. I do want to say, Hayden, there are not 5 experts here. There's only 4 space experts, and one of us is just a weird, crazy guy with weird hair. But the cat was the star. That's for sure. Took control of the situation, didn't he? Now, we have a question here from Kevin. What current space observation or exploration results are you interested in seeing in the near future? You can include theoretical developments as well. So who'd like to go first on that one? That's a nice... They're all just like...
I can start.
Yeah, go. Yep.
So sort of very exciting news in the field that I work in, which is, galaxies in the early universe. And the real sort of big telescope that we've all been waiting for a very long time now is the James Webb Space Telescope, which is sort of a successor to Hubble. Bigger, sort of able to look at a wider range of wavelengths. And so hopefully we'll be able to get much higher resolution. Much better observations basically of galaxies in the early universe, as well as so many other different fields like exoplanets, all these things that require sort of very high detail observations. So it was due to be launched this year, and I was expecting that they would have to, delay it again because of COVID and everything. But actually, it's had a launch date confirmed, which I think is December, late December, basically, just before Christmas. So that's really exciting, and hopefully that'll take some time to get to the point where it's going to be observing from, which is actually not in orbit around the Earth like Hubble and most of our telescopes are, but it's actually a decent way away from the Earth, sort of on the other side of the moon's orbit, essentially. Not quite, but sort of far away. And so next year it's going to be taking what's called early release science observations. So just testing that all of the telescopes, sort of optics and technology has sort of survived the launch and the trip to space. And then, in the next couple of years, it's going to start to actually take these observations for, the things we want to be looking at. And so I'm really excited to see what's going to be coming out of that. It's only got a 5-year window of time that it's going to be working. So because Hubble is in orbit, it was much easier to do sort of service missions and expand its technology. But with James Webb Space Telescope, because it's so far away, we can't really go and fix it if anything goes wrong. So there's really a sense of crossing our fingers that it's going to survive the launch and then nothing's going to go wrong. But yeah, I mean, it's a really amazing instrument. I think it's going to make some really amazing discoveries in a whole range of different fields of astronomy.
I'm going to totally jump in there, Steffi, because for me, being a quasar...
Oh, we're losing you again, Claire.
Galaxies with... I give up, honestly.
No, you're back, you're working.
Oh, only because I'm annoyed, right? Threaten. So I'm a quasar person. And the quasars are supermassive black holes at the center of galaxies that are very hungry. So they're eating a lot of material around the accretion disk that's falling in at a high rate. So these galaxies are what we call active galaxies. And James Webb is actually going to look at 6 of the furthest quasars that we know about. They're from a time when the universe was sort of less than 800 million years ago. So that's 6% of its current age. And we still don't really understand a lot about how these supermassive black hole accretion rates interact with the way that these galaxies have sort of star formation and how they grow. And these galaxies are huge, and we still don't really understand why we've got these huge galaxies, 800 million years old universe. It's not almost not enough time. So there's some really fundamental questions about how galaxies form so quickly, where these supermassive black holes come from in the first place. And then there's all the interactions between other galaxies and the material in between these galaxies at such an early age. So I'm really excited because this is sort of my wheelhouse, probably not quasars. I really only look at a redshift of around 0.6. But yeah.
We got all that just in before you froze again. That was good. Do you have an answer to this as well?
Yeah, absolutely. I want to reiterate a little bit about JWST, and in particular what Claire was talking about with the very distant quasars, because this is not something I work on, but for me, understanding how in the world these supermassive black holes formed in such an early state of the universe is one of the big open questions. There's no good answer to that at the moment, as far as I can see. But I think whatever the answer is will be certainly very interesting from a theoretical perspective, and understanding the evolution of the universe in those first few 100 million years. Having said that, there's some other things that excite me even more, and this is a little bit more from my field. When we look out into the universe, as far as we can possibly look using any form of light, the furthest back we can see is not 800 million years after the Big Bang, but it's 300,000 years after the Big Bang. It's really close to the Big Bang itself. But we can never use light to look further back in the universe than 300,000 years ago, 300,000 years after the Big Bang, because the universe was opaque to light at that point. But there are actually ways of doing it, and there is both neutrino astronomy and also gravitational wave astronomy that can potentially look back to the universe when it was less than 1 second old. And so that is what excites me. We're not there yet, and we don't know when we'll get there. But we hope to be able to look at the universe when it was on the order of a second old, in ways that we have no chance of being able to do any other way. And so for me, that's one of the really exciting things that hopefully will come out of especially gravitational wave astronomy in the next decade or less.
That's actually seriously impressive. It's maths and science that I'd never ever understand, but it would be amazing to be around if and when that was made possible. Yeah, that's mind-blowing stuff.
Agreed.
Yeah. On the note of mind-blowing stuff, Stefan, do you have any current space observation exploration results you're interested in?
Yeah, I think a little bit of a cop-out. I'm going to say James Webb Space Telescope as well. I think that's something we can all get excited about. But for me, it's actually one specific aspect of the James Webb Space Telescope, and that is the investigation of the spectroscopy of exoplanet transits. So I'm actually a chemistry student, and so I'm interested in a bit more of the chemistry of some of the astronomical bodies that are out there. And James Webb Space Telescope is going to allow us to essentially measure take spectra of the atmospheres of exoplanets as they transit in front of their stars. So that's something that I'm really excited for, to learn a bit more about the chemistry of some of the other worlds that are out there, and potentially make a really interesting discovery and find some fascinating new chemistries.
Hopefully we answered Kevin's questions. We've got a much more complex one now, so you're going to have to get your thinking hats on. Andrew, who's very, very, very good at his planetary astronomy, wants to know, one thing that has troubled me somewhat is the concept of inflation of the early universe, which doesn't seem to have any scientific basis other than it makes the equations work. I'm happy with concepts of abstract theories, but I do prefer them to have some scientific basis behind them. Do you think we will come up with a better theory than inflation? Who wants to tackle? Oh, Paul wants to tackle it.
I want to, because it flows on exactly from what I was talking about before with looking at the universe 1 second after the Big Bang. So it's true that cosmology without inflation, cosmic inflation at the moment. Actually, let's step back a second. What is inflation for people who aren't familiar with it? If you think about cosmology, and we've talked a lot about the universe is expanding, things are moving further away from us, the further away they are. If you actually analyze just in the what's called standard cosmology framework, this paradigm, then you actually come up with a lot of paradoxes. One paradox is, for example, I talked about that the universe, when it was 300,000 years old, it's opaque to matter. And actually, when you look at that quote unquote surface 300,000 years after the Big Bang, it's incredibly uniform in temperature. I think it's uniform in temperature to 1 part in about 10 to the 5. And there is, not only is there no good reason for that without inflation, but actually 2 different regions of that universe were causally disseparated at that point. And so this is one of many paradoxes. What cosmic inflation does is it says when the universe was much less than a second old, it actually underwent this huge period of really, really rapid expansion, exponential expansion. And it did so for sort of 10 to the minus 20 seconds or something, just a pretty short amount of time, but it solves all of these problems in a really, really neat way. Now, it's true at the moment that all we have as far as inflation is concerned is that it solves these paradoxes, and it is the only good theory that we have that solves these paradoxes. Absolutely, that's true. That said, it does make testable predictions and is therefore a scientific theory. One of those testable predictions is things like gravitational waves in the early universe. It predicts what gravitational waves should look like. They should, first of all, be seeable by gravitational wave experiments, but they should also you should be able to see the imprint of them on the cosmic microwave background when you look at polarization measurements and things along those lines. So while I completely take the point of the question that, can we be happy with this because it just is a theory that works and doesn't do any better at the moment, it is absolutely a scientific theory because it makes scientific predictions that are testable and we can test them. The fact that we don't have the technology to test them yet doesn't mean it's wrong, and doesn't mean there'll be anything better. Now, I'm part theorist, part observer. I'm probably more theorist. Absolutely, we should be striving to come up with alternatives which also have testable predictions, and then we can play them off against each other and see which one works better. But I think there's actually nothing wrong with the theory of cosmic inflation until we prove that there is something wrong with the theory of cosmic inflation. I hope that answers the question without being too aggressive.
No, that was actually a very good answer. Even I understood that. That says you did it well. Did anybody else want to add anything to what Paul has just said, or we think we've covered that one well enough? Yeah. All right. So this is all right. So I'm trying to jump around to. We've got quite a few questions here, which is great. So Katie wants to know, will the Hubble Space Telescope still be operational and used once James Webb Telescope is launched? So is it going to be gone and forgotten like the AC's 25-inch telescope, which hardly ever gets used because we've got that fancy 40-inch one there now? Sometimes it's good to go back to the old dudes.
I'll jump in here.
Yep.
So one of the very cool things I think about the Hubble Space Telescope is actually that it was only designed to be used for 10 years, and it's already 31 years old this year. So the fact that it's still working at all, I think, is really a sort of marvel. And part of that is because, as I said before, since it's in orbit around the Earth, when we had the shuttle program from NASA, it could be sort of serviced easily and have new cameras sort of installed regularly. So of course, the shuttle's not, the program has been shut down for a long time now. And so Hubble now is sort of, starting to sort of fall apart. You may have heard, I think about a month ago, actually, it just stopped working and had to be, there was a few weeks when it was not operational. It had to be sort of fixed by people in the US. And so I do expect that sort of thing to happen more and more often. There's certainly particular cameras that are not working quite as well as they used to, just because things break down over time. This entropy that you might have heard of definitely applies to technology. But people are very much, still Hubble is in extremely high demand. The program that I work on at Melbourne Uni, we still have people in our sort of collaboration that are still, proposing to use Hubble for various different observations. So the fact that James Webb is going to be launched, it has different instruments. It's a different telescope designed to look at different things. So, and same with all telescopes on Earth. Each telescope has its own particular set of cameras, spectrographs, all that sort of thing, which make it really useful for one thing over another. And part of being an observer is trying to work out, what's the best way to take these particular observations that I want to take, which telescope is the best. And there's certainly lots of applications where Hubble is still the best telescope to be able to do particular types of observations. So as long as it works, people are going to keep using it. Hopefully it works for another 10 years. I don't know that it will get that long, but certainly at least for the next couple of years, while James Webb is sort of ramping up into its main observational program, Hubble is going to sort of be along for the ride as well.
Hubble also, really good explanation, Steffi. Also, along with normal entropy, I mean, it's exposed to the space environment as well. And people always think, space is empty, it's fine, there's nothing there. But there's a lot of radiation and cosmic particles that come through space that we're protected from, through our magnetic fields and our atmosphere and all those sorts of things. So it's actually quite a harsh environment up there, and things do break down, and they do suffer attrition. And they do get damaged, but also most orbits decay over time. And so as far as I'm aware, Hubble's actually destined to come down in a fiery descent and break up in the atmosphere at sort of mid-2030, I think, without any sort of, I guess, severe intervention. But I agree with you, Steffi. I think it's likely to be mostly defunct by that stage. Yeah.
So will they keep it around long enough for it to make sure that James Webb is obviously working well? And if something goes wrong with James Webb, obviously they'll try and use Hubble for as long as they can. Because if you send that one up there and it's too far out to be repaired and something goes wrong with it, like what happened with Hubble, then all of a sudden we've got nothing. So
they'll just keep using Hubble at the same time. Yeah. They'll just use Hubble. And no, they'll just keep using Hubble until Hubble dies. So it's not about, as I think what Steffi also was saying, is that it's not really about not using Hubble until we get JWST. It's about using JWST for everything it was designed for, assuming it does work and it doesn't have any problems, knock on wood. But also there's no reason for us to not keep using Hubble until it dies. There's no reason we wouldn't use them simultaneously. It's basically not when I say not costing anything, it costs vastly more to put it up there in the first place. And to just leave it to die for no reason, if it's actually still usable, would be pointless. So there's still science that can be done. And if it's still got the instruments working, then there's no reason they wouldn't keep using it until it is dead.
But just something that Mark, you just said, that if James Webb doesn't work and Hubble sort of also breaks down, then we are really just out of luck. So there's certainly we're lucky that observations can be taken in like visible wavelengths that we see with our eyes from the Earth, but there's certain wavelengths that just don't make it through the atmosphere. As Claire sort of was saying, the atmosphere protects us from a lot of harmful rays, but sometimes we want to use those different wavelengths to look at different objects. And so there was the Hitomi telescope, which was an X-ray telescope that sort of broke apart when it was orbiting, I think about 5 years ago now. And the loss of that satellite really left, X-ray observers with just nothing, no telescope that they could actually use, because the previous generation had already sort of worn out and broken down. So if James Webb doesn't work and then Hubble sort of breaks down over the next few years, we are really going to have a bit of a hole. Fortunately, we have lots of telescopes on the ground that can do similar things, just not quite as efficiently, not quite as well. So we're not completely out of luck, but yeah, it would be a really massive blow, I would say, to lose one of those telescopes.
Can I ask from the JWST experts, what sets the 5-year timescale? Is that going to be a hard limit, or is there a chance it'll be like Hubble that it lasts for a lot longer? What actually determines that 5 years?
Yeah, so I wouldn't say it's necessarily a hard limit. The problem is that telescopes need to be very cold, because if they're hot, then you have, or room temperature even, all the electrons that are making the electronics work, they let out what we call thermal radiation, which is just, infrared light essentially. And if you're taking infrared observations, which James Webb is meant to be doing, then that's really going to affect your observations by giving you a lot of extra light that you don't want. So you have to keep your telescope cool. And when it's in space, you're limited with how much coolant you can actually take up there. So a telescope like the Herschel telescope, which was mid-infrared, so even longer wavelengths, that only had 3 years of coolant, and really, it lasted for 3 years, and then it just had to stop taking observations. So so James Webb has the sun shield, which should hopefully, prevent, extra light from the sun hitting it, which Hubble doesn't have really. And that may sort of extend its life a little bit. But I think everyone who works on James Webb, or things that they want to use James Webb for, is expecting that it will be 5 years only. And, if it lasts longer, then that's good. But don't expect it to.
I think it's also about the fuel to keep it in orbit, right? So the amount of fuel it's actually got to stop the orbit degrading, as far as I understand. I don't know a lot about it.
Yeah, all those sort of things that go into the planning. Ideally it will last for 10 years, but 5 years is sort of what we expect, I would say. And anything else is a bonus.
Cool. All right. Covered that one nicely, didn't we? Couple other ones. Oh, actually, there's quite a lot of questions. We might not get to all of them, but we'll do our best. Following on, I guess, from James Webb a little bit, kind of. Are Voyager-type space missions planned in the present or future? So there are any other missions similar to what we did with Voyager planned or likely to be planned that we know of?
I know of one.
Yeah.
So just first of all, in case anybody doesn't know, the Voyager missions went past the planets and then went out to explore past the limits of our solar system and out and beyond. China actually have one in the mix called the Interstellar Express or Interstellar Heliosphere probe. And the idea of this IHP, and so they're looking at doing it, they're saying 2024, but I just never know. Basically, sort of outside the sort of solar system is this sort of gas bubble. So the sun is constantly streaming out all these solar particles, and that goes all the way through the solar system, and it hits, it's called the heliosphere, and then it sort of hits out into interstellar space. And so what this IHP, the Interstellar Heliosphere probe, is doing is going to do a flyby past Neptune, and then it's actually going to push out into this region where this the sun's sort of reach with these particles kind of hits the don't worry, Steffi, we've all got our own animal problems going on over here, where the particles actually sort of hit this boundary, I think called the heliopause, and essentially trying to go out there and have a look at pushing sort of our knowledge of what's happening just outside our solar system, which is just another one of the things that China's achieving in space. I think they've just been incredible over the last decade or two with the things that they have done and achieved everywhere. It's just been insane. So I think that's probably one to watch.
There's that, I don't know much about it. There's that, is it Starshot, Slingshot, Star Moon, Star, the breakthrough, I think it's Starshot.
Oh, the breakthrough projects. They're cool.
Yeah. Where they want to actually send up little 1 centimeter square sized things that are powered. This all just sounds very Austin Powers-esque. They're powered by laser beams they're powered, but actually like laser beams from the Earth, I believe, that provides basically energy from the photons that hit the back of this thing and accelerates them to close to the speed of light. And then they're trying to get them out to Alpha Centauri, I believe. And to say it's a technological challenge is underselling it.
Starshot breakthrough initiatives. There we go.
Yeah, that's
Now,
it. They've got a
it's
bunch of
only-
breakthroughs. There's Breakthrough Listen, Breakthrough. There's a whole bunch of other ones as well. They're really awesome programs, and these are what they call the proof of concept for a nanoscale, nano spacecraft, which sounds cool.
Yeah.
It only is Austin Powers if the lasers are on the back of sharks.
Lasers.
Laser sharks. Actually, that's getting a bit Lego movie as well. Now, a couple more questions. So we got Robert wants to know, will the universe ever stop expanding or will gravity pull it back in? I'm going to throw this one first to Stefan and then let everyone else jump in afterwards because Stefan's been sitting quietly in the background for a while since he answered his last question. It's your turn. Step up, young man.
Oh, that's a big one too. Look, I'm just going to defer to the experts on this one. As I understand it, there are a few potential futures for the universe, and it sort of depends on the large-scale structure of the universe. As far as I understand, we could be headed for a big crunch, a big rip, or an eventual heat death. But I'll leave the details to those who can give them.
Steve told me to do that. Payback for last night. Who wants to take that one on? I think, Steffi, you were talking a bit about this on
Yeah,
Wednesday
so I think I
night,
mentioned
weren't
this
you?
sort of in talk on Wednesday. So this question, so when I was a kid and I would read a lot of astronomy sort of textbooks and things back in the 90s, this question is really something that was sort of discussed because it was really an unresolved question. So whether the universe keeps expanding or whether gravity sort of starts to pull it back in really depends on how dense the universe is. And so at that time, we didn't really have a good understanding of just how dense the universe is. In the 1990s, this thing called dark energy was discovered, which is basically this sort of energy that's sort of permeating the universe and opposes gravity. And now that we have, lots of different ways of measuring how dense the universe is, I think what what the consensus is probably that the universe will continue to expand indefinitely, essentially. So there's just not enough matter for the gravitational force. As I mentioned, everything, is gravitationally attracted to everything else. So there's just not enough material for that gravitational force to really start to pull the universe together. So what the sort of continued expansion means is that everything's going to move away from everything else, aside from things that are already in some sort of gravity, like we call it a gravitational well, but you can think of as like, a cluster of galaxies. Those sort of things, the gravity is strong enough that they will stay together, but everything else is going to keep moving apart. And so as everything's moving apart, the universe starts to get cooler and cooler. So the background temperature of the universe at the moment is about 3 degrees above absolute zero. And so it'll get colder and colder really until, there's just no material left to form stars. They'll all burn out. Everything will just sort of cool down eventually. And so this is called like the heat death or sort of freezing of the universe, which I think is sort of the most common sort of theory at the moment. Certainly the one that I think is the most likely.
Does anybody else want to add anything to that? I think that was a nice, deep, in-depth answer. I think we might well have covered that one off nicely. What have we got? Hayden wants to come back for his first question. Following on from his first question, if it's space that is expanding, he thought it was a vacuum. Can a vacuum expand? If so, can you explain it in a little bit more depth? Thank you. So we're talking before. Is that one? I think we might have flawed our experts with this one.
No, look, it's a tough one to think about, and you can use analogies, and I will use an analogy, but the analogies all fall down. Realistically, you can go back and look at the equations, and absolutely, the entire universe, it is the space that's expanding. It has nothing to do with whether it's a vacuum or not. It doesn't matter whether there's matter in that or not. When Einstein told us that that four-dimensional space-time is the thing that governs the dynamics of the universe, and it is that space-time that's expanding. The analogy that we like to think about when we think about gravity in general is put a bowling ball on a trampoline. It's this old one, and the trampoline bends because of the mass, and it is then, in this expansion sense, it is that trampoline that's expanding and that's getting bigger and bigger and bigger. Again, that's an analogy that if you push it too hard, it'll break down. And so it's not good to think about it in too much detail, because you'll get problems with it. But it doesn't have anything to do with whether the universe is a vacuum or not. Probably you can start thinking about whether dark energy is the vacuum energy of the universe, and you come up with an even bigger problem in physics. You do a small little calculation, and you end up 120 orders of magnitude wrong. So let's sweep that one under the rug. But realistically, whether it's a vacuum or whether it's anything else, it is the space-time that is expanding. It's this four-dimensional geometry of the universe, and it is that's expanding.
Can I just jump in there for just a moment and just step back and just talk about a vacuum for a second? All a vacuum means, I think it's taken on this sort of magical aura to itself, this idea of space being a vacuum. Basically, we can create almost vacuums on Earth. All it means is that within that area that we're talking about, there are no particles, or effectively very few. So space is not theoretically a vacuum anyway, not really vacuum anyway. There are particles, zipping in and out. And there are also, the odd molecule floating past, the odd piece of gas, hydrogen, whatever. There's always something around. And as I said, particles will zip in and out due to quantum effects, which we don't need to go into. But the idea that a vacuum is some sort of magical thing is actually not true. All it means is that it's a space that has no particles in it. It has no gas, no solids, nothing inside it. It's got nothing. So the idea, as just to reiterate what Paul was saying and explain really, really well, is that we imagine the actual fabric of space-time. So it's not like a particle of hydrogen or a piece of dust. It's the actual being that it's in, the sort of fabric that it exists in, which, again, I was talking about this earlier, for me is one of those mind-boggling things, because you can't really imagine it, and all analogies fall down. But just be really careful about the definition of a vacuum. They're really not that special.
Yeah, it's like how darkness is just an absence of light, right? There's nothing so exciting about it. It's just when it's dark, there's just no light. When there's a vacuum, there's just no matter. It's an absence of matter.
I think we've covered that one off nicely as well. The only thing I can add to that is that a vacuum is the thing that cleans the house for me. On that note, that was my bad dad joke, I know. What is the most profound image captured by Hubble for each of the panel, and why? Who wants to go first? Who wants to pick the one that everybody else might pick before they pick it?
I'm happy to, but I'm talking a lot.
Well, no
Go on,
one's
Steph.
complaining.
The same thing.
Go on, Stefan, you go first. You go first.
Yeah.
Sure. So I was just actually looking up the name of it. I can't remember the name of the object. Here it is. So the object itself is V838 Monocerotis, and it's stunning to me because it's an example of something that we call a light echo. And so the object itself, I believe it's the remnants surrounding a dying or dead star. So there's some matter in a sphere around this star, and I should have looked into the details about this beforehand, but essentially,
everyone else look into the details of your photo.
it's a fantastic photo. So if you're in the audience, look up V838 Monocerotis. So yeah, there it is. And the coolest thing about this is that over the period that this image was taken, some of the light from the star had actually moved out and illuminated more of the surroundings. And so in the period of, I think, 10 or 20 years, you can actually see the light moving through this structure, and it seems to change. It looks like the object itself is expanding, but it's just an optical illusion, really. It's just the light moving through an existing object there. But Mark, if you've got that image up, if you can look up the video of this or a GIF of it, you'll see it, and it's just fantastic. It really sort of it's something so cool. And another example of these are what are called Hubble variable nebulae. These are nebulae which have a variable star embedded in them. These variable stars sort of, they vary in their luminosity, their brightness. And because of this, they sort of send out waves of light through these nebulae in periodic ways. And it looks like the nebula is shimmering itself. Just fantastic. Really, really cool. That's stuff that always stands out to me, is not just static images, but when things are sort of changing and moving, it really brings it to life.
I have been sent that link, so I'm going to try and get that going. Who'd like to start talking about? Here we go. Yep. All right, I've got it. We'd have to stop sharing that one and share a different screen now. That's actually a very cool little. This is it here.
Yeah, how cool is that?
So
it looks like that's the cloud actually expanding out. But if that were the case, it would be expanding much faster than the speed of light. In reality, it's just the light emitted from the progenitor star that's moving through and illuminating the surroundings. So I think that was over the duration of 10 or 20 years, something like that.
That's very cool. All right, now next, Paul, you can go next. I'm just going in order of who's off my screen. So, Paul, what's your object for Hubble?
Hubble Ultra Deep Field, without a doubt for me. Basically, I think the Ultra Deep Field is the second version of what was originally called the Deep Field. The Hubble Deep Field, and essentially someone just had some spare. Oh, there we go. Look at this, even better tech. Stefan's got it on his wall.
I was just
showing the old-fashioned way.
Yeah,
showing the old-fashioned way. All right.
So it looks like a bunch of blobs, right? But
we'll do it the modern way now, shall we? Here we go. Here's the modern way. There we go. Wonder if I can make that bigger. How's that?
Lovely. So what's remarkable about this image is, I think this was the second version of them, but essentially some people just decided that they would use some spare Hubble cycles, some spare Hubble time, to just stare at an empty patch of space. And the first time this was done, it was, if we just stare at an empty patch of space for long enough, collect enough photons, we basically won't see anything because it's an empty patch of space. But of course, the longer you stare, the more photons you collect. And what you see is that at every patch of space, you're just looking deeper and deeper and deeper. And so each one of these tiny dots is not a star because it's an empty patch of space, at least in our local galaxy, not just local galaxy, but local cluster and even further out. So these are incredibly distant galaxies. And clusters of galaxies and all of these things, and it's just what that represents to me is just mind blowing.
Now, Stephanie, what's your object? And
Yeah, so
I'll go hunting for it.
that's all right, I'll send you the link. So I talked a lot about the Hubble Deep Field at my talk on Wednesday, so I chose something different. So back in 2014, when I was sort of a master's student, there's this really exciting discovery called supernova ref star, which is the first multiply lensed supernova. And so a supernova is basically a star that reaches the end of its life and explodes and makes an extremely bright, so basically point of light that fades over the course of a month or longer, depending on the type of supernova. And so this one was discovered behind a galaxy cluster, which you can see in the image that Mark is showing on the screen. And so galaxy clusters, because they're just so massive, they're made up of, hundreds of galaxies often. They actually warp space-time, and so light that's coming from behind it, the path that light is coming from, if we're on the Earth and we shoot a laser, it goes in a straight path. But if we were behind a galaxy cluster and shot a laser, it might get deflected sort of and come around the cluster. And so that magnifies the brightness of objects that are behind the cluster. And it also means that light that's coming from that object behind it, it tends to go on different paths. And so depending on the path that it's going, the space-time might be more warped than a different path, which means that different images can take longer basically to reach us from the same point in the sky, because the light is traveling at different different lengths basically. And so this is the first time that this was actually observed for a supernova. So the first one, the first image, and this supernova is really, really long way away. So to use this sort of magnification technique, you have to have, something between you and the object that you're looking at. So the object you're looking at tends to be very, very far away. So this is around 9 billion years, like light years away. And so the first one, I think, is the sort of original image, the colored one. And then you can see the supernova in the images on the right, the black and white ones. And so the way that, depending on how long it takes for each individual image to turn up, that tells us a bit about, the lensing properties of this cluster. And that allows us to get an idea of, what the actual structure of the cluster is. Tells us a bit about, space-time and bending, which tells us a bit about, relativity, gravitational lensing, all these sort of things, which was really, really sort of groundbreaking at the time, and just not possible to do without Hubble, because it's got this incredibly detailed resolution that allows you to see this individual supernova behind these large galaxies. So that's my one.
That actually answered one of the other questions that was going to be put up, which is wonderful. So that's one less question we have to worry about answering. Now, Claire, your image, what image has Hubble taken that you think is the best?
Steffi, snap. Mine is grav lensing too. But of course, because I'm a quasar girl, I've sent Mark the link in the chat, so I'm sure he's bringing it up right now.
Yes, there we go.
Yeah, so this is a really cool image. Sorry, give me a sec. This is a really, really cool image of basically a quasar being lensed by two foreground galaxies. So this is a quasar with the wonderfully memorable name 2M1310-1714. You probably can't call your kids that, even though it is a fantastic name. So what you're seeing here, and Mark, I don't know if you can magnify your screen a little bit or whatever, but right in the center there, you can see this ring of light with 4 distinct dots around the ring. You can just make out probably 2 really bright sources inside that circle. And so those 2 really bright dots are the galaxies, the foreground galaxies. They're relatively close to Earth compared to the quasar in the background. But those 4 dots around in the ring, and also Hubble data also showed that there was another 5th, and this is very, very rare, a 5th image of the quasar in the center as well. So there's actually 5 points of light in there that actually are the one quasar. So what Steffi was talking about before with gravitational lensing, we often get these with distant quasars where two sort of galaxies which have enough mass to bend the light around them, much like a lens does in your glasses. It takes the light from the quasar into different paths, and you get these 4, or in this case 5 different separate images of the one quasar. And so this quasar is absolutely ages away. This quasar, so these galaxies are about 3.8 billion light years away, but this quasar is heaps further away than those galaxies. It's in Virgo. It's in the constellation of Virgo, and it's about 17 billion light years away, this quasar. So one of the great things about gravitational lensing is it actually allows us to see objects in the universe that are much further away than we could see without it. So they're almost like lenses in your glasses. And for me, just being able to reach those sorts of distances is just phenomenal. Being able to look at quasars so far away, and because I'm a spectra person, of course, all I want to do is just, split that light up and take a spectrum of it and have a look at the physics.
I think that's for very unique images from a Hubble point of view. I all thought you were going to do Pillars of Creation, to be honest. It's a little bit too overdone, isn't it? Couple more questions before we finish up. I think we might be able to get 3 more in. There's a lot more questions. If any of you guys on the panel want to jump into the Facebook or YouTube chat later on and answer some of these questions, you can, because there's quite a few interesting ones. We have... let me find it. Where am I up to now? I've lost it. Tim Tam wants to know, if black holes are just dead stars, how come they're not visible to the naked eye?
I'll take this one quickly.
Yep.
We see things because they shine light. Black holes are black. So as Paul said before, in a dark room, no light. That's dark because there is no light. So black holes don't actually give off any of their own light. So we can't actually see them. The sort of, I guess, exception to that is in the work that I do, which is supermassive black holes with a bunch of material in a disk around outside the black hole. That material spins and it has to lose angular momentum. So it has to lose its spin as it falls into the black hole, which means the energy has to be radiated out somehow. And so we can see light from this accretion disk, which is very close to the black hole, and sort of infer the movement of material around that and work out that it has to be something with a lot of mass but only a very small radius, so we can infer that it's a black hole. But we can't actually get any light from that black hole itself because black holes do not emit light.
There we go. Next question. We're going back to James Webb again. Is there a plan for a successor to the James Webb Space Telescope in the works? If it's only going to be there for 5 years and Hubble's going to be plummeting into Earth in 2030-ish or thereabouts, what are we going to use? Is there something else now being planned, and will it take 10 times longer than James Webb did to get ready to get up there?
I could jump in. So definitely, yes, people are making plans for like a successor for James Webb, but they're also currently making plans for space telescopes that will go up sort of concurrently with James Webb. So a lot of them are to fill in some of the gaps that James Webb doesn't cover. So James Webb is designed to take really high resolution images with a small field of view. And so some of the telescopes, I think it's Nancy Roman Space Telescope, which is also being developed by NASA, is designed to look at similar wavelengths but take wide field images. And so that means it can cover a lot more of the sky than James Webb does at a lower resolution, but it means that you can look at a large patch of the sky with the Roman telescope and then move to the James Webb telescope to look in more detail. And so there's certainly other ones with similar sort of ideas of either looking at different fields of view or different wavelengths. So there's the LUVOIR, which is I think it's meant to cover UV, optical, and infrared, which is where the name comes from. Because these are all sort of wavelengths that are easy to look at from space. So yeah, certainly there are lots of different telescopes being developed all the time. It's just what actually gets funding to take a look at. So usually NASA will have one sort of planetary satellite, and then one sort of large telescope sort of in development, and then smaller things. And of course, there's other countries that develop telescopes. So I mentioned there's a Japanese telescope looking at X-rays that blew up. Claire's mentioned, I think, Chinese sort of telescopes. So yeah, and Europe, of course, is also building different telescopes. So yeah, certainly specifics for a successor to JWST. I'm not sure if that's really in the sort of plans that much, because James Webb hasn't been launched. But yeah, people are sort of trying to get new telescopes up all the time. Yeah.
There we go. Now, I think we'll do 2 more questions. I'm going to pick them nicely for this one. I think is an interesting one. What are some of the most likely applications for plasma in the future with regards to astronomy? A lot of puzzled faces there.
Heating the Earth. Does that count?
Should I just?
Well, that's in any form to do with astronomy that you can think of.
And the sun is a plasma, so it heats the Earth. I'm going with that.
I was thinking
else?
about plasma transfusions, for blood, because I always give plasma. I'm joking. I don't really know about that one. Does anybody have any? I mean, there's nothing that's special about plasma, really. It's just it's a bunch of charged particles that sort of is very sort of magnetic and electrically active, I guess.
So is there a way of using those charged particles for space exploration?
Well, okay, so actually something's just come to my mind. I was actually interviewed about this a long time ago. There was a guy that wrote a book about somebody who was writing a plasmoid car, was designing a plasmoid car. I think the idea of actually using plasmoids for propulsion at the moment is not, it's not really realized. So if that's kind of where you're going with that, I think that's quite a long way into the future, possibly not a real thing. But yeah, it's hard to know without more information what sort of plasma application we're talking about.
All right, we'll move on to another one. John, is not the end of the universe when entropy is 1? This is also a theory from some scientists. Energy goes from low entropy to high entropy. Maximum is 1.
But it only ever approaches it exponentially, so I don't think you ever get there. It asymptotes. So I don't think that's mathematically a valid or correct statement.
Can we just explain just quickly for people what entropy is, just because I know that some people like a few, just some explanations. So entropy is essentially, if you use the word entropy, replace it with the word disorder to first order. So one of the things that, you get told is to cut the spine off, War and Peace, throw it in the air, collect the pages. Some are still going to be in order. Some of them will be a little bit out of order. Do it again. You're increasing the disorder every single time you do that. You pick it up. And the idea is that it gets less and less likely. Well, over time, it's unlikely that it will trend back to order. So it trends towards disorder over time. And that's what the idea of entropy is this trend towards a disorder in the universe. So every time, so when you spill a glass on the floor, for example, the water goes from collected in a glass to being scattered, and it's actually very hard to pick up and put it back in the glass spontaneously. If that makes sense. Did that?
Yep.
Paul's looking up in the sky, so I'm hoping that was an okay explanation.
No, no, I don't. You don't want to know what I was looking. I was looking up dimensions of entropy because I think. So I think your explanation was perfect, Claire.
Okay, good. That's all right. I thought there was a cat or something.
No, I have another monitor up here.
You're actually secretly looking at cats, aren't you? Entropy cat.
Yeah, I'm jealous of all the cats that everyone else has.
I don't have a
And the
cat.
Pavlova discussion.
Oh,
I'm
yes,
not-
we've had a bit of
Yeah,
that.
God.
Now, one last question, which I think we can go with. What have we got? Gunnar wants to know, have astronomers or have factored in how dark matter and dark energy will decide the fate of the universe? So when we're talking about from a scientific point of view, not from an astronomy point of view, I dare say, from a scientific point of view, has dark matter and dark energy been factored into the explanations that people have given for how the universe is going to end?
Yeah, so I think I took this before, so I can sort of elaborate.
Yep.
So yes, definitely. So the discovery of dark matter back in the 70s really changed how our understanding of the universe's sort of history took place, because we discovered that 80% of the matter in the universe is actually this dark matter that we weren't taking into account before. And same with dark energy when it was discovered back in the 90s. So dark energy, I would say, is the more mysterious of the two. But definitely its effect on how the universe has been expanding, in its history, because we can't really observe what's going to happen in the future. All we can do is take what we can see using our sort of universe time travel telescope and see at different points in the universe what the expansion history was like at that point. So definitely, yes, the fact that the expansion of the universe is accelerating due to the effect of dark energy has definitely been taken into account when we make theories about how the universe is going to, you can say, end or continue in the future. So this big freeze or sort of heat death is taking into account the fact that dark energy is going to continue to accelerate the expansion of the universe, because there's nothing that we've seen between dark matter and our baryonic matter, which is what we call basically the things that light interact with. So all of our stars and planets and galaxies. There's not enough of that really to counteract what dark energy is doing to the universe. So yes, definitely it's been taken into account.
I think we can finish on a rather sad note for astronomy. If expansion keeps on going and everything gets further apart and cools down and goes dark, then what are future astronomers going to look at? Nothing.
Also, it's going to take a very, very long time for that to happen.
Yes, a very, very long time.
It's going to be well after, our own sun has evolved into a red giant and probably consumed the Earth. So, whatever alien astronomers are in, billions and billion years in the future, they're likely to see, their own galaxies that they're in. If they're in one, of course, we can have stars and planets that are not inside galaxies. They'll see their own galaxy and any other galaxies that are sort of gravitationally attracted to that galaxy. So like their cluster, but yes, everything else that's sort of beyond that is likely to get pushed beyond, our observable universe. So yeah, it is a bit sad to think about.
Can I say what's sadder to think about is that there's not going to be that many future astronomers if we don't get climate change under control? Am I allowed to throw in a political?
You can throw in anything you want to throw in.
Excellent. I don't think we should be worried too much about whether astronomers are around to see the heat death of the universe, because I think we've got bigger fish to fry.
Our own heat death to worry about, right?
Yeah.
Correct.
Our own heat death, yes. I would agree with that completely. Now, I think that's pretty much it. So we've gone a little bit longer than we had anticipated, but that's because we had so many questions. We didn't get to them all. So some of them are on YouTube. Some of the comments are on Facebook. If you guys...
Mark, I reckon it's really important that maybe Paul or Steffi or whoever wants to, not me, answers Tony's, whatever. I've spoken so much. Tony's question, just because I think that's something that people struggle with a lot.
Sorry, I
in
didn't even
terms
see
of
that one.
Look back time, light travel time, and
let's do one
cosmological
last
age.
one. Yes.
Sorry, I'm going to throw you guys into it.
That's right. There we go. If the universe is some 13.5 billion years old, we'll finish on this one then. How can we say something is 17 billion light years away? There hasn't been that much time to travel to us, or has there, relatively speaking?
All yours, Steph. It's a great question.
It is. I'm trying to think of. I get this question a lot with my undergraduate students, and I'm trying to think of how I usually explain it to them. So we have the universe is this 13.6 or 13.7 billion years old, and so the universe is expanding. And so when we look at so we have this thing called the Hubble Law, which is when we look at galaxies that are outside of our own, we take a spectrum of them. The particular elements in that spectrum are not exactly where we would expect them to be based on our lab experiments here on Earth. And this is because they're moving away from us. And this sort of movement is sort of the first evidence for expansion. And so as we look at more distant galaxies, they're moving faster, basically. And it actually doesn't take very long before this velocity that the galaxies are traveling becomes greater than the speed of light. And so my students will get very confused as to how this is happening, because of course I've told them that the speed of light is the fastest thing in the universe. And so this is sort of a it is a I may be looking up something right now. That's fine. And so this is sort of a one of these things where we just have to understand that, yes, the universe is expanding, but as I said, I literally just said that the galaxies are moving away from us, but it's not that the galaxies are moving away sort of their own volition. It's that the space between them is expanding. And as there's more and more space, that expansion sort of increases. So the I don't know if there's a very good explanation. Sorry, everyone. As there's more space, the expansion sort of adds up, which gives you that higher velocity. And so, but it's not that the galaxy is moving itself at this speed greater than the speed of light. So we have this thing called the observable universe, which is that because the universe was smaller in the past, it is possible sort of for us to observe things that are sort of further away than this 13 billion light years. And so the observable universe is, I think, actually about 90 billion light years across from memory. And this is really just because, it's sort of, it's hard to explain. I don't know.
So Steffi, sorry to jump in for a sec. If you thought about I was just thinking about how you're explaining it, and it just occurred to me that maybe this might help. If you had let's say you had an expanding loaf of bread, and you had an ant that started at one edge of the loaf of bread. Okay, and this is not a complete analogy because we're not talking about an edge of the universe or anything. But if it starts at the outside of this loaf of bread, and this bread keeps expanding, right? The idea isn't that it just expands once and it's linear. It's the fact that it expands, and then all the pieces that are made then expand themselves, and then expand themselves, and then expand themselves, right? So it's actually each time, if you want to think about each particle getting made, you make 3 particles, each particle makes 3 particles, do you know what I mean? So it keeps getting expanded within that section. So you've got this loaf of bread expanding, and the time of the loaf of bread expanding is very different to that ant. So that ant's like, oh, I've got this far to go. And then next minute, it's actually got this far to go. And then next minute, it's got this far to go, right? And so this poor ant that's got this speed has actually got a lot further to go, and it's traveling, and it's not necessarily related to the actual expansion of the loaf. Does that make sense?
Yeah, I think it's
ants and loaves. I've had an ant problem in the past 3 weeks. Can you tell? Talcum powder, that's where it's at.
I'm surprised you didn't use pavlova or cheesecake as the example, to be honest.
Yeah, just for the people that don't know, we have a private chat, and a lot of it has been about pavlova today.
So just some of what I was saying. The galaxies themselves are not moving with this superluminal speed. It's more that the universe is expanding, and the universe is not bound by that speed of light rule. So it's sort of like the addition of all of the different sort of distance between us and a galaxy very far away is making it look like it's traveling more than the speed of light, but it's not that the galaxy itself is moving at the speed of light. It's just that space is expanding so much that the light has to, travel a really long time to get to us, and it looks, as a result of this expansion, it looks like it's traveling very fast. Yeah,
That's a
very good question.
Tony says that analogy helps, and says it's like being stuck on a treadmill, going nowhere fast. So that's a very good analogy. Well, I just want to say thank you to you guys for being here today. Thank you, Claire. Thank you, Steffi. Thank you, Stefan. Thank you, Paul. And thank you to our viewers for all of the wonderful questions. We hope you learned something interesting about astronomy and deep space. We will be back this afternoon for our final stream, which covers topics of new astronomy. So for those of you who are new to astronomy, we have our new astronomy group's section director, Ken Lamarckland, who's going to talk about, well, all things new with astronomy and how to get into it and what to expect and steps to learn how to, I guess, view objects, things like that. So we'll be back at 4 o'clock. I'm going to go and have some lunch now before I start again. If you haven't subscribed, please subscribe to our YouTube. If you are not on our Facebook, please follow us on Facebook. And thank you to everybody who donated stars on Facebook today. It's greatly appreciated. I'll see you in about another hour and a bit. See you later.